Okay, so we'll continue our discussion of the FEM. So what we have seen so far is this idea that FEM is the weighted residual method, and we discussed some very simple requirements on the weighting functions. Basically that the functions and their derivatives should be square integrable over the domain, and the other is that they must obey the boundary conditions. Okay. So, with this having been established, let's look at one of the very key steps of this FEM, which is converting to what is called a weak form. Okay. So, what we'll do is we'll consider two steps which will help us to accomplish this thing. Okay. So, let's go back to our equation. So, if you notice our equation over here, let's look at this one term over here. So, it seems to be a double derivative, right? And there is a w function next to it, right. So, let us look at step 1. Okay. So, I have an integration over the domain of Wm. I have Wm of x, okay, and this first term is d by dx. Okay. There is a px d by dx of ux. Okay. I am just writing only the first term. Okay. So, looking at this, is there some simplification you can think of? Because right now if I open this up, what am I going to get? I am going to get a derivative of p and a second derivative of u, right. Second derivatives are of course, given a choice you would rather not deal with higher order derivatives, better to deal with lower order derivatives. So, what can you, looking at this form, what does it tell you? So, it is d by dx of this whole thing. So, is there any trick that comes to mind? What about integration by parts? If I do integration by parts, I have to integrate one function and I already have the differential inside there. So, this seems to be tailor made for integration by parts with this guy as the first function and this guy as the second. So, what happens of this term? So, the first term will simply become, so this w will remain here, w remains as it is. This becomes px d by dx of ux and evaluated at the end points. Okay. I will just write end points, the limits of integration basically. And then what happens to the other term? So, minus I have a derivative of the second function multiplied by, so I can just write it here, this is one term, and then I have px into derivative of ux by dx. Okay. So, step 1 was basically integration by parts. Okay. So, integration by parts is what has given us this simplification. Now, this looks very simple to do in 1D. It is actually very simple to do in higher dimensions also, except that instead of a d by dx, you will have a del operator. That is the only difference, and we will look at that in 2D when we come to 2D. But notice, apart from ease of integration, what have you actually done? You have, in some sense, if you look at this expression, you have transferred one derivative from u onto w, right. This derivative which was acting here on px and u prime x has now been transferred onto w. Okay. And that gives a nice kind of symmetry, because you know, before we even get into it, you know that in FEM, Wm and Um, they are going to be chosen from the same family, right. It is Galerkin's method, the testing function and the basis function is the same. So, I have to only worry about Wm and its derivatives. No higher order term is coming over here, because it is only du by dx, not d2u by dx2. Okay. So, this was step 1, and the step 2 is very simple. Substitute this into the original equation. Okay. Whatever trick we did integration by parts, we substituted back in. Okay. So, when we substitute this, we can write this as, let us look back at our original form over here. So, first term we have dealt with, now I have the second term over here and this third term over here. Okay. All of it weighted by the weighing function Wm. Okay. So, let us write this out. So, the first term I am going to write as omega m. So I'm writing this guy as the first term now, d by dx of wmx, okay, first term, px dux by dx. First term is taken care of. Second term was qx ux. So this will be a plus wmx qx ux, okay, and there was a minus fx term over here, that's the third term. So that appears over here as minus wmx fx whole thing dx, okay. So I'll just write this a little bit carefully. The minus sign is only for this term. Is equal, okay, and plus, now I'll write the endpoint terms, wm x px du by dx equal to 0. Okay. This looks very long, but I mean it was very clear what we did, right? We had wmx into the residual equal to 0. That was what we did, and this residual was nothing but this d by dx of px du by dx plus qx ux minus f of x. This was my residual, right? So the first term is what I did in step 1, integration by parts, simplified it, transferred one derivative from u onto w as a result of doing that. Second and third term remain as they are, they get multiplied by a wm on both sides. Okay, yeah.
So in the residual term, the first term was minus p by dx.
Yeah, so the minus is here.
No, I mean term rx is actually minus p by dx, as you told us.
Rx is oh, there's a minus sign over there. Oh, right, there's a minus sign over here. So let's look over here. Okay, so when I substitute this, right, this will become minus and this will become minus. Yeah, and this also is a minus. Yeah, that was the original Rx, right? Yeah, thanks for pointing it out. So all the minus signs are fine now, right? Okay. And this I should write a little bit more carefully. This is at the endpoints. The first term in integration by parts. Okay. So everyone has followed the trick that we have done. It's just integration by parts, that's all. Okay. Now this longish looking equation that we have written over here, this is what is called the weak form of FEM. Why is it called the weak form? Any guesses? What is weak about it? Not the order of derivatives, it's simply weak because I'm not enforcing at every point in the domain, I'm enforcing it in a weighted sense over some interval, so it's called the weak form, that's all. But this is the form that we will use to convert into a numerical solution. Once I've transferred the second derivative into a first derivative, okay. So that is the first thing, this is the weak form, okay, that is the first thing I want to mention. The second thing is, notice that this one equation has inbuilt into it information about the entire problem, not just the differential equation but the boundary conditions also. How is that? The endpoints, right? So I have, so the boundary conditions appear in this equation. How do they appear? Because I have to substitute the value, I mean I need to know what is the behavior of u or du by dx at the endpoints, and that gets substituted over here. So typically this is a term which is known, it has to be. Boundary conditions in a 1D case simply means endpoints x naught and xn, whatever, right? So this that's another sort of nice aspect about this equation, that the differential equation and the boundary conditions both have appeared into this in one shot. Okay. It's fine? Okay.